guys had a wonderful, very restful break. So, we have a week left, basically. Hi. Yeah, there's something wrong with the campus Wi-Fi today. I don't know what to tell you. You're all gonna be marked as absent. No, let's see what happens. If there's a problem, I'll remove this class from the accounts. Okay, but I do want to get started because this is we have fun stuff to talk about today. So, what we're gonna do today is we're actually gonna go kind of on a fun journey where we're gonna introduce this new concept, and then we're gonna see it play out in both a theoretical context and a practical context as well. All right, so let's get started because actually there's quite a bit to do today. So here's the premise. This is the only thing I'm not gonna explain today. I'm just gonna ask you guys to trust me and believe me that there does exist a function. By a function, I'm talking about just a function that I can call, a Java function that I can pass some inputs and receive some outputs. But really, you know, think of this as a mathematical function that exists in the world, has the following properties, okay? The first one is that if I call it with the same arguments, I get the same result. It's deterministic. It's not that unusual for functions to be deterministic. The second one is that if I look at the output values that I get back, let's say that this function returns an int. If I pass it lots of different inputs, the probability of giving every different possible Java int is roughly the same. So essentially the output from this function looks random, except for the fact that, as I pointed out on the first part of the slide, it is deterministic. Last step is the output should be easy to compute. This function should be easy to compute. It's not computationally intensive, okay? We will come back later and revisit this last requirement, but for now, these are my requirements. Function that's deterministic. Every output from the function is uniformly likely, so it's uniform. And finally, the function is also fast to compute, okay? What I'm describing here is something that's known as a hash function. A hash function takes, and there's whole families of these. You can find many, many different types of hash functions if you follow that link or Google around. But a hash function is any function that takes an arbitrary amount of data. Think of this as like a string of arbitrary length, okay? So I can hash like one text message. I can hash the entire record of the Library of Congress for 2018, or Congress, or whatever, some big thing. So the input can be any amount of data. The output is a single value. This is known as the hash value, sometimes just called the hash, sometimes referred to as a digest. To be honest, if someone could turn off that buzzing, that would be great, actually. The Wi-Fi, I don't know, but that, did anyone hear that? Or is it just me? Maybe I'm losing my hearing. All right. Anyway, we'll try to soldier on here. So this is a real thing. There's a whole, again, I said there's whole families of these, okay? So what we're gonna do for the rest of the day, I'm not gonna talk about hash functions. You might learn a little bit more about them in later CS courses, in terms of some of their theoretical properties, maybe even look at a few implementations of hash functions, which are kind of wild. But what we're gonna do for the rest of the day is we're gonna talk about what we could do with such a function. Because the thing we're talking about is actually the hash that's part of hash code. So this is actually one of the things that's built into all Java objects. You might wonder why, what's good about this, what's useful about it. We'll get there. But let's see some things that I could do with such a function, okay? If one existed, and in fact these do exist. All right, so let me point out several ways in which hash functions are useful, and these are actually ways in which they're used in the real world. You guys encounter these all the time, you don't realize it. Once you start looking at the results of hash functions, you might start to recognize them more. You see them around a lot, okay? Even if you don't know what you're looking at. But let's imagine the following scenario. So you need to download some big file to your computer. Maybe you need to do that to install some piece of software or something like that, okay? Now here's the problem. It's possible that the file that you download at some point gets corrupted. Maybe in its journey across the internet, one of the bits in the file gets flipped, okay? And what that means is when you go to install it, it could crash, it could fail, it could do bad things. So you wanna make sure that the file that you downloaded from wherever, this ginormous file, is the correct file. You want some sense that every single bit of that file is correct, okay? So here's what you can do, okay? So let's say you don't have a hash function, all right? Well, what do we have to do? Well, we download the file once, so we sit there, and you know, your internet's fast now when it's up, right? But in the past, maybe, you know, this might have taken like a few hours. So you go, you have coffee with a friend, you come back, and then what's your option here? Well, download it again. So now I get to wait again. And then I have to compare the two and make sure that they're the same. And so the idea here is that if I download the file twice, then I have some sense that if I got the same file twice, then that's the version of the file I'm supposed to get. Now, this approach has other problems I'm not gonna get into, but this is kind of the best that you can do. All right? But remember that I have this magic function that has these properties. I can run it over an arbitrary amount of data. It returns me some value, a hash value. It's deterministic, so I give it the same data, I get the same value twice, and it's fast, relatively fast to compute. So let's go back and think about how I can do this with a hash function. So I download, first of all, I need a hash of the copy of the file, right? So I download the file, I compute my hash. I use this hash function, I give it all the contents in the file, every single bit, and it returns a value. I'll show you one of them in a minute. And then what I can do is I can either download the hash or I can go to the website, and a lot of times the website will have a hash code listed, and I can compare the two hashes. If the two hashes are the same, but these hashes are small. It's like an int, like a long, long integer value, like a long value in Java or something like that. It's just a big number, but it's still small. It's way smaller than the file, okay? Now I compare the two hash values, and if they're the same, I've concluded that the file that I downloaded is correct. Okay? This makes sense to everybody? So I'm utilizing a couple of the properties of the hash function here. One is that it's efficient to compute. If it was really slow to compute the hash of the file, I might as well just download it again. The second property I'm using is that it's deterministic. So if I run it on the file and somebody else runs it on the exactly same file, we should get the exactly same result. The other property about it being uniform, I'm also using, because if the hash function returned the same value every time, then I wouldn't know whether I got the right file or not, because every file would have the same hash value. But the idea is that there's a lot of different results of the hash function, and each one of them is roughly equally likely. So if I hash a lot of files, I only get the same hash value if the two files are the same. And we'll talk more about this in a minute, because it starts to depend on features of the hash. All right, so let me give you an example of this in practice. So this is a real website where you can go to. You can download something called LaTeX. Anyone heard of LaTeX before? This is a formatting tool for writing scientific documents. It's, well, don't get me started on LaTeX. But anyway, people use it. So this is a place where you can download a version of it for Mac OS, which is what I use. And what you'll see down here is that this is a 4 gigabyte file. And what's listed right below that file is something called the MD5 sum. This is a hash value. MD5 is a hash algorithm. So what this site is saying is that after you download this file, if you run MD5 on it and compute the hash using the MD5 algorithm, here is the value that you're going to get. And it's this long, this is a hexadecimal value, okay? It's an integer, it's just in hexadecimal notation. That's why you see the few letters mixed in there. And you can do this. This is the way to validate that you got the right file. You download the file, you have this MD5 program installed on your computer, you run it on the file, it finishes in a couple of seconds, and if it spits out that value, then you got the right file, okay? So again, MD5 is you know, and I can do this. So here's an example of me just doing this on my own computer, right? So actually, this is a new version of MacTeX. This is from 2018 or something. At the time, we were expecting this MD5 hash value. I ran the MD5 program, I told it to hash the contents of this big package that I just downloaded that I don't want to download again, and it gives me a result. All right, so now here's another place where we can use hash codes, or hash functions. So the hash function is a function of the contents of the file. So if the contents of the file change, the hash function is also going to change. So imagine that at some point you sent me a document, you know, and I'm not gonna open this document because it's a Microsoft Office document and I don't know what to do with those anyway, but imagine that I did need to open this for some reason, and, but I can't remember if you sent me the latest version. I don't know if I have the latest version of the file, okay? Now people in the normal people in the world have come up with all sorts of really terrible ways to solve this problem, right? They give the file name like they give the file a name that has a date in it, or they have a version, or there's like, you know, Susanna's version 5, 2019, you know, 1022 or something like that, right? But we have a hash function, right? And we know what we can do with it. So without a hash function, you just have to send me the file again, and then maybe I need to figure out a way to kind of look at the differences between the two of them to see if they're the same, right? If I have a hash function that has these properties, what you can do is you can compute the hash of your file, and I can compute the hash of my file. If the two hashes are the same, we have the same file, okay? And again, we're gonna talk about the reason why this property holds in a minute, because you might think, well, if your hash value only has is only like 8 numbers, it's like an int that can only store 8 values, then how is this possibly true? But we'll talk about that in a minute, okay? So the hash codes that you use for this have this property where if the two hashes are the same, the file contents are identical. You will only get the same result from the hash function if you run it with the same inputs, okay? If the files are the same, we're done. Otherwise, you send me your copy, okay? So, you might have, when we saw that MD5 hash code a minute ago, something might have, little bell might have gone off in your head. You might have started seeing something that looks like that before, right? Where have you seen this? You've seen this in Git. So internally, Git uses hash codes, and I think it uses an algorithm called SHA-1, maybe. Somebody can look this up. It might have changed recently. So it's a different hash function than MD5, but the principles are exactly the same, okay? And you see these. The commit IDs that you see on GitHub, those are hash values, okay? So over here on the right side, this is a commit, and the thing that identifies the commit to Git is a hash code. That hash value incorporates the contents of the commit and all of the contents of your project at the time that you made that commit. So even if you commit the same contents twice in Git, you're gonna get 2 different commit hashes because it also includes things like the timestamp and stuff like that, okay? But this is how internally, this is how Git identifies everything. Yeah, it is SHA-1, look, it's on the slide. So if you start to think about how does Git work, right? How does Git detect that a file is changed and things like this? It's all done using hash functions. Internally, everything that Git thinks about is in terms of hash functions. That's how it figures out if a file is the same as a file that, you know, it figures out if you modified a file. This is how it figures out if a file moved around, right? If you move a file from one place to another and you don't change it, what Git realizes is, hey, the file contents are the same, but the name of the file is different, and it just makes a note of that in its database. All right, this is also how Git push works. So when you push your code to submit it, you push it to GitHub, it doesn't transfer all of the contents of your repository every time. That would be really slow. So the question is, how does the server, how does your computer and the GitHub server, what's the protocol they use to figure out what new information you have that GitHub.com does not? The way this is done is using a protocol that uses hashes. So roughly, your computer says, I have a repository that has the following contents, and it kind of lists all the hashes of the stuff that it has. And the server looks at its copy of the repository and it says, okay, well, I've already got some of this stuff, right? So I've got whatever object has this hash, but I don't have those other 2 objects. Those could be files, those could be commits, whatever. And then what happens is your computer sends those along. So that's how Git push works. That's why if you Git push and then you Git push again, nothing happens. There's no new information to send. So again, here we're using a hash function, with this special function, with these special properties, to essentially fingerprint content. And this happens all over the place. I was, over the break, I was helping my wife, who's a photographer, with some of her photos that we have on some sort of rickety storage system. And I was poking around in Lightroom, which is the program that she uses, and it computes these previews of the photos that are in your library, and it stores those previews identified by hash code. So you can find it's like directory, and they're all sorted, and the names are all hash values, essentially, of the contents of the file. Okay. So now let's talk about collisions. So this, the good thing about hash functions is that, I can use them to do all this cool stuff, but you might be wondering what happens if two things, two files in Git, two photos in my wife's photo library, which has like 60,000 photos in it, two files that you downloaded have the same hash value. What happens if they hash to the same value? So this is known as a collision. Depending on what we're doing with the hash, this can either be a problem or not. It really depends. So in some of the scenarios I just identified, it's clearly a problem. So for example, if Git encounters two files that hash to the same value, its universe is going to explode. It cannot handle this. I'm serious. Like, if this, like, Git is completely designed around the assumption that this will never happen, okay? And it uses a hash function that's been configured to make sure that it's very, very, very unlikely. But trust me, if this ever happens, you will read about it, it'll be on the top of Hacker News and stuff like that. People find two files that actually have the same, different files that have the same SHA-1 hash value, right? And then they'll show you all the terrible things that happen to Git, once this takes place. All right. So again, in some cases, if we've decided that the output of our hash function is small, we expect collisions and we have to be ready for it. If the hash value is large enough, then essentially we do not expect any collisions at all. And if the hash function is uniform, right? So again, Git will essentially totally melt down if this happens, okay? So this brings us to a fun little puzzle, actually. So this is a fun, how many people have heard of the birthday paradox before? Fun little math puzzle, a little, probability-based puzzle for you. Okay. So, imagine I have 100 people. What is the probability, actually, imagine I have, 600, 700 people, how many people are here today? What's the probability that there are, well, let's say with 100. 100's more fun, because with you guys, it's like there's only 365 days in the year, so the probability that two of you have the same birthday is clearly very high, right? What about if I only have 100 students, okay? What's the probability that two of them have the same birthday? Anybody want to take a guess? Yeah. 50%, okay. I don't know, I mean, to me it's kinda like, there's 365 days in the year, there's 100 people, so it seems like it should be like a third or something like that. Anybody wanna make other guesses? Just flip forward on the side and get to the answer. It's like almost 100%. Why is this? Well, one thing that's important to note here, this is not the probability that two people have the same birthday on a specific day. It's the probability that any two people have the same birthday. We don't know what day it is. It could be any one of the 365 days in the year. So with 100 people, so now, another variant of this. How many people do you need to get to the point where there's a 50% chance that a group with that size will have two people with the same birthday? Okay, so with 100 people, it's like, the probability is almost 100%. With 50 people, it's gonna be smaller. With two people, it's obviously pretty small, but how many people do I need to get to 50%? Flipping a coin. 23. Yeah, so if I took 23 of you, I took another group of 23, probability, one of you was probably gonna have a birthday in common, the other one might not, right? But it's only 23 people. So, on some level, why are we talking about this? We're talking about it because this is essentially the same thing as the hash function having a collision, okay? So, imagine that the hash function, let's say that my hash function has 365 outputs. It's like days of the year. My hash function hashes to days of the year. So I give it an input and it picks a day of the year as the output. I give it another input, it picks another day of the year. I only have to give it 23 inputs before there's a 50% probability that I have a collision. 2 of them have ended up on the same day. So this is bad for our hash functions. Essentially, the result of this exercise is to try to convince you that collisions are much more likely than you think. You might think that they're unlikely, but it turns out I don't need very many people before I have this collision, based on the birthday paradox, okay? So again, if I put this in slightly different terms, how many documents do I have to hash before I have 2 with the same hash with 50% probability? Well, now here's the thing. The answer to this question depends on the size of the hash output. How large of a value is my hash function producing, okay? So this is entirely a parameter that we can choose to determine how likely collisions are going to be. If we want collisions to be very, 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 very unlikely, we choose a hash function that produces a large value. If we don't mind collisions, we might choose a hash function that produces a smaller value, okay? So if my hash function produces a 16-bit outcome, 16-bit result, that means there's 2 to the 16 possible results, then I only need 300 files before the probability of a collision is 50%. So would this work for something like Git? No way. I mean, you know, a couple semesters ago, the MP6 starter code had 80 files in it, right? I didn't compute how many files were in the starter code for this semester's machine project, but it was probably over 100, okay? Like the Linux source code probably has like hundreds of thousands of versions of files in it, right? So this is clearly not okay. So let's try bigger, okay? What about 32 bits? So if the result of my hash function is 32 bits, now I can hash like 78,000 documents, okay, before I have a collision. Still not very many, right? My computer has like over 2 million files on it, okay? A lot of these are probably on your computer too. They're like files the system needs to operate. I didn't create these files, okay? All right, what about a 64-bit hash function, okay? Well, now we're up to 5 billion. So this is the number of files that I can hash before I have a collision with 50% probability, okay? Now again, a collision is bad here for some of these programs. Like for Git, it's just meltdown time, right? So we really need the probability of a collision to be tiny, okay? So for 64 bits, we're up to 5 billion files, but we don't want the probability of a collision to be anywhere close to 50% or 1% or 0.1%. It has to be like as close to 0 as we're willing to accommodate, okay? GitHub.com at the time that I wrote the slide had 1 billion files. It's probably up to like 2 or 3 by now, okay? So this is not okay. All right. As we continue to increase the size of the hash function, now we're starting to get into the realm of where we feel comfortable, okay? So for 128 bits, this is 14 times some really big number. I don't know, what is this? Let's see, billions, trillions. I don't know, I don't go past trillion. It's big, right? However, Git actually uses a 160-bit hash function, okay? So essentially, and if I go all the way to 512 bits, so if the output of my hash function is 512 bits, now I have roughly 10 times less. I can hash like the number of atoms in the universe divided by 10. So every 10th atom can have a hash code. That's probably enough. But again, Git uses 160. I actually didn't do the calculation for 160, but you could do that. Okay, and actually again, if we go back, let's go back and look. Just go back and peek at our GitHub page. So again, over here on the right, you can see the full hash value for this commit, okay? This is hex, so every character is 16 character is 16 bits, yep, it's 0 through 16. So you can count the number of those and divide by 16, and you'll get a number that works out to the number of bits that Git is using. Okay, questions about this before we go on? All right, cool. So up to this point, our interest in hash functions has sort of been purely theoretical, but let's make this more practical, okay? So what I'm gonna introduce you to now is probably I would argue, I mean, one of the single most useful data structures in computer science. Okay, you've already seen one of the most useful, which is a list. A list was a generalization of an array. Remember arrays a long time ago? Lists were like arrays with a couple more features, but this is a linear data structure. It allows me to put things in order, but essentially really what I'm doing, if you think about what an array is doing, an array associates an additional piece of metadata with every item in it. I have, remember, data and metadata. So the data is what's stored in the array. Here the data is the numbers 5, 6, and 7. The metadata is that they're in that order. And the metadata is also the index associated with each value. So I'm associating a piece of metadata 0 with the piece of data 5. I associate a piece of metadata 1 with the piece of data 6. This is the index in the array. So arrays are mapping an index to a value, okay? That index has, so the values I put in my arrays can be anything. We've worked with lists of numbers, we've worked with lists of strings, you can work with lists of objects or whatever. I can put anything into a list or an array. But my indices had to be integers. So every index in my array had to be an integer. There was no way to use like a string as an index. Until now. Okay. So what Java calls this incredibly useful data structure is a map. And that's a reasonable term for this. It maps one type of value to another type of value, when either one of those can be any type of Java object. Okay, so we're gonna work with this a little bit in the playground in a second. But essentially a map allows me to use any Java object like an array index. Now unfortunately in Java, the map syntax is kinda gross. It's a little bit like an array list. This is fixed in other languages. It's also fixed in other more kind of modern Java-like languages. But here's how we work with a map in Java. So I'm importing both the map and the hash map packages. This is very much like list and array list. List is the interface, array list is an implementation. So map is an interface, hash map is an implementation of that interface that uses hashes to behind the scenes, and we'll see how that works in a minute. All right, so here what I'm doing is I'm declaring a new variable called string values, and this uses that generic syntax that we looked at when we looked at lists. We're gonna talk more about generics later this week. So this says I'm declaring a map, and that map is gonna map strings to integers. So the indices in this array, quote unquote, are going to be strings. The values are going to be integers. Sometimes we call this the key and the value in the map, okay? So using a key allows me to get to a particular value, all right? And then I, create my new hash map over here. And now what I can do is I can put values, I can create mappings. So put associates a key with the value. So essentially put says, this map will map test, the string, to the value 5. And then later, if I want, I can get the value of test, okay? Same thing here. So I'm gonna put test, now I'm gonna associate it with a new value. This is like overwriting the index in an array. And now I'm gonna get that value back. So again, this is like an array. The syntax is different. So maybe it's better to think of it sort of like an array list, where instead of, get and set, I have put and get. Put creates a new key value mapping. Get gets the value for a particular key. So again, these are, maps are possibly one of the most useful data structures out there. They are built into a lot of other languages, and they are prettier in a lot of other languages. All right, so in Python, here's what a map looks like. So again, this looks a lot like an array in Java, right? I've got square bracket syntax, except what I have inside the square bracket is a string. So I can do this. This is valid Python. JavaScript looks almost identical. In JavaScript, these are actually technically anonymous objects, but who cares? It's not that important. C++ has something called a map. The syntax is gross, but it's C++, so that's what you get. Go has maps. Perl. Anyone? I won't even ask. An old language that is dying a well-deserved death. But it had them. It had maps. That was actually one of the things that was really good about Perl at the time. They're terrible. Look at that syntax. I mean, you think Java syntax is bad, right? There is no reason that the $ needs to be there, except that it helps you remember it's a map. All right, so anyway, Kotlin has maps. The map syntax in Kotlin is really nice. All right, so here's our map interface. Let's just play with these guys a little bit, all right? So, and let's use our generic syntax here, right? So here's what I'm gonna do. Let's create that map that we were just using that maps from strings to integers. And over here I need to use my diamond notation to just tell Java that I wanna create a hash map that also maps from strings to integers, okay? And now let's put something into this. Let's do map example dot put test, and then I'm gonna do 5, and then I'll print out the result of pulling that value out. All right, good. So this kind of work as expected. The types in my generic declaration allow the compiler to help me here, like I was talking about before. So for example, if I try to put something into my map that is not an integer, I'm gonna get a compiler error telling me that I can't do that. I told Java that my map, called map example, is gonna map from strings to integers. I'm trying to create a map from strings to strings. If I want that to work, I can change the declaration, okay? I can also map from integers to strings, in which case I need to change the key, and then my get statement down here as well. Okay. There we go. All right. So, let's do a problem with maps, just for fun. And this is one of those places where there are certain problems, in fact, there are a lot of problems, where maps are just so useful. Like, they're so clean, right? There's really no other, better way to solve some of these problems, okay? So this is like the classic first use of maps, which is, let's say I have a big chunk of text. And what I wanna do is I wanna pre-process the text so that I can very quickly answer queries about how often a particular word occurs. So I'm gonna give you like a big chunk of, I don't know, transcript of something. And you can take some time to work on it, you know, set up things properly. And then I wanna be able to ask you, like, how many times does the word the appear? How many times does the word whatever appear? That's what I wanna be able to do. All right. So here's our little example that we're gonna fill in together. What I'm doing is I'm creating a class called word counter. And what it does is it takes an array of words. This is the text that I'm passing. And what I'm gonna do in my constructor is I'm actually gonna do some work to set up this map so that it has the right entries in it. And then my get word count function is gonna be very simple, okay? So I've already broken the text into strings for you. So you don't have to do that. I'm giving you an array of strings. What I want you to do is count them, okay? All right, so what I did in my constructor, I declared a private map that's gonna map from strings to integers. So whenever you work with maps in Java, you wanna think about what am I mapping from and what am I mapping to. Here, the thing I wanna be able to look up is a string. The result that I'm gonna get back is an integer. It's a count, all right? So now let's do the following. So here's what we're gonna do. We're gonna say for word, let's see if I can write some Java code on the first day back after break. All right, so I'm gonna go through my array. And then what I need to do is essentially, I want to increase the value to 1 if this key exists in my map, okay? And this is a little bit tricky to do, so let's go back and look at the map interface again for some help. And you guys can go over this in your own time, right? So if I go down to put, where'd it go? There it is, okay? Actually, what I want here is get, okay? So there's this, get will normally fail if I give it a value that's not in the map, right? So it returns null if the key isn't already in the map. In this case, I don't want null back. What I want is 0, okay? I want to be able to basically retrieve the current value from the map and add 1 to it. But there's also this very helpful get or default method. So what that'll do is it'll essentially look up the key. If the key's in the map, I get the value that is associated with that key. If the key's not in the map, I get some value that I can pass into this function, right? All right, so let's do this. So let's do word count dot get or default. I'm gonna look up my word. And if the value's not in the map yet, the initial value is 0, right? Okay, so we're gonna save this. I'll call this current count. And then what I'm gonna do is I'm gonna do word count dot put for word current count plus plus. Okay. So again, 2 things. I'm retrieving the current count of the number of words times that word has already appeared in the document. If it's never appeared before, I get 0. And then I put it back into the map, but I add 1 to it, okay? So let's see if this is gonna work for me. Okay. So now let's see if this worked. So my get word count method takes a string to look for, and what's supposed to return is the value of that string. So again, I could use get here, but get's gonna return null if this word isn't in the document. So instead, what I'm gonna do is simply return word count.get or default word 0. So it's the default value. If the word is missing, should be 0. All right. Let me try this. There we go. Okay. Oh, plus plus. Almost fooled by that. Okay. So let's see what happens here. I passed in here, here, there, and then I do 3 lookups. And actually, let's do this. And then, it's just so we know what query is being run here when it actually runs. Oh, come back here. There, okay. So I have successfully counted words. Super exciting. Okay, let's just make sure this works. Let's change this to nowhere. Make sure it gets counted now, it does. Any questions about this example? Imagine what you would have had to do here to solve this using just arrays or even lists. It is horrendous. So this is a massive improvement in terms of our ability to solve certain types of problems in Java, okay? All right, questions on maps. You guys will get a little bit of practice this week on the homework working with maps. Yeah. Why didn't plus plus work? Ah, great question. Okay. Who's ready for some Java trivia? I just want to point out, there are evil people in the world that actually put stuff like this, like, on quizzes and stuff like that. I've seen, like, intro CS exams that had this type of question on it, which I think is just like, but, yeah, you know, it does sometimes cause problems. So what goes on here? Why doesn't this work? This won't work. Let's try running it. Yeah. Why doesn't this work? Anybody know? Yeah. Oh, you're close. Yeah. Right. So let's do this. Oh no, now it hates me. No, I want to try to get it after here. No, it's no way it's gonna do that. Yeah, I'm trying to be too clever here. Yeah, so here's another example. So this does work. So, I can't believe we're talking about this today, but yeah, there it is. When you use one of these, and this is actually something that's worth knowing, right? It's one of these little gotchas with Java. and there's several other languages that work this way. When you use a decrement plus, a post plus plus, what happens is Java uses the value for the current expression. So current count gets used in word count.put, and then it gets incremented. So what happens here is the current count, let's say it's the first time I've seen the word. Current count starts off at 0. I run line 10. I run line 10 with current count as 0, and then I set it to 1. So it never gets incremented. So let's do this. Let's do current count plus plus, and then we'll put it in. How about that? This works fine, right? Why? Because line 10 increments current count, and then I put it in a separate statement, right? So by the time I get to line 11, it's already been incremented. Good question. All right. So now for fun. That's basically the last week of class. So we're gonna have some fun. Let's think about how we would actually build one of these things. We've built a list, right? We built a list in a couple of different ways, but how are we going to build a map? Okay? So how do I implement a map? Now, you normally wouldn't implement a map, you just use hash map, and there's several other maps you can use that are built into Java. But thinking about how one of these works is actually kind of fun. And it'll give us a chance to not only look at some cool code, but also think about big O analysis. So this brings together a lot of the things that we've been doing recently. All right, so the first step is to realize that Java objects have a built-in hash function. So hash code, that, remember we talked about the 3 functions that are provided by big O object that we don't think about very often? One of them was equals. Another was, there are 2 that we think about a lot, equals and toString. There was a third one that we were gonna come to at the end of the semester. Well, here we are. Hash code. So hash code will actually return a hash code for the object. So that's what we're gonna use, okay? Now, there are no guarantees about this hash code not providing very many collisions. So we're gonna have to think about what to do about collisions. So here's how we're gonna use the hash code value. The first thing we're gonna do is we're gonna take it, and we're going to take a small part of it. We'll essentially do a modulus to convert it to something with a much smaller range, like maybe something between like 0 and 7, so 8 values, okay? And then we're gonna use that as an index into an array. But how do we handle collisions, okay? So this is what's so cool about this particular implementation of a map, okay? I'm combining 2 data structures that you guys have seen already this semester. So here's what happens in my map. This map has, you can see, 12 different slots. This keeps going on. So when I put something into my map, I take the hash code, I use it to figure out which slot it's gonna go into in my array. If it's the only item in that slot, I'm fine, I just add it. But if there are other items that have already hashed into that bucket, is sometimes what we call it, what I do is I chain them together using a linked list. So I have this combination where the front part of my map is an array, the back part is a linked list. Okay? And it turns out that I actually get a little bit of the performance of both depending on the size of each of them relative to each other. I'll come back and explain what I mean by that in a minute, okay? So here is our implementation of a hash map. This actually works, okay? I don't have time to go through it carefully, but we'll come back and talk about this a little bit on Wednesday. So let's look at put, okay? So what does put actually do? Let's start on line 23. So the first thing I need to do is figure out where it goes in my array. Actually, we should start out by looking at some of the private members of the class. So up at the top here, I have a constant that determines how large my array is, okay? So I'm gonna set it to 16. This is similar to my linked list. I have an inner class here called item that I'm using to store each item. And this looks a lot like the item that I used when I built a linked list because it is the exactly same thing. The same item class, okay? I have a key, I have it's not the same item class, it's slightly different. It has one additional thing, which is the key. When I put something into a map, I associate a key with it, right? A key and a value. So every item has the key and the value that were associated with when I put it into the map. And then it has a next reference to another item. So this is how I chain them together. All right? My class has a little private method called hash that it uses to take the hash code. So see, I'm calling hash code. And then what I'm doing is I'm doing a modulus based on the size of the table. So that's gonna give me a number, in this case, between 0 and 15, inclusive. I could change that if I change the size of my table size. And then here I'm handling the irritating fact that the modulus operator in Java can return negative values. Okay. So now let's go again. Let's go through put, step by step here. So the first thing is I use hash code. I call my hash function. That uses hash code of the object that is my key to figure out which bucket it should go into. Then what I'm gonna do is, what am I doing here? This actually looks a lot like walking a linked list, because that's what I'm doing. I set my current reference to the first thing in my array in that slot, and then I go through the entire list. It's possible this list has no items. What I'm doing here is I'm looking for a object in the map that already has the same key. If I find that object, I'm gonna change the value. I'm not gonna create a new object. So if I find a place where current.key equals the key that I'm putting, I just change the value that's already in my map. Otherwise, what I do is I add the item to the front of the bucket. So I create a new item, I have its next reference refer to the items that were already in the bucket, and then I change the start of the bucket to refer to the new item. And then I have this count that I'm keeping, which returns the number, which I use to keep track of how many things are in my map. Okay? So does this work? I don't know if it works, because we haven't implemented get yet. And I think that's a homework problem this week. So it does seem to work in the sense that it's maintaining the count properly. So here what I do is I put a value in for the key test. I map test to me. After that point, I have one item in the map. Here, I put test and I change the mapping to another, and then I still only have one item in the map. So clearly, put seems to be able to find previous items in the map that I already put in with the same key, and and change their value rather than add a new item. All right, so I'm gonna, well, you know what, let's do this and then we'll review this on Wednesday. So let's think about the performance of our map, okay? So first of all, if the array is very small, so let's say my array only has like 2 buckets. Let's say my array only has 1 bucket in it. That essentially when I have to walk all the way through the entire list. If the array is small, that list contains roughly O(n), where n is the number of items in the map. Get is also gonna be O(n), because I'm gonna have to go through that same list. So essentially, when my array gets small, my map starts to behave like a linked list, okay? Now let's imagine the array is extremely large, so the probability of collisions is very small. So now when I put an item into the map, it's usually the only item in that bucket. And when I get it out, it's also usually the only item in that bucket. And so I get constant time performance because I'm essentially doing gets and sets into an array, which is constant time, okay? So at this point, my hash map is acting essentially like an array, okay? It seems like this is better, right? O(1) is faster than O(n). What's the problem here with making the array really big? Why not just make the array massive, and then I'll never have collisions and the performance will be great? What's the trade-off? Why wouldn't I just do this? Yeah. It takes a lot of memory. And a lot of that array is, let's say my map has 4 items in it and my array has 24 slots. Most of the array is empty. So it's a waste of space. All right, we'll pick up here on Wednesday. I have a couple of important announcements as you guys are getting up. So Probably the most important one is that the assignment, the final project checkpoint is tomorrow, okay? That's 10% of the final project grade assessed tomorrow based on how well you guys have gotten started. If you need help, come to office hours today. I will see you guys on Wednesday.